Have you ever wondered how the inner product of two vectors is calculated and what it signifies? Well, the inner product, or dot product, is a key operation in linear algebra. It takes two vectors and outputs a scalar. It's like the dot product in Euclidean space, but more generalized. Geometrically, it's the projection of one vector onto another, meaning it measures the overlap between the two vectors. Algebraically, it's the sum of the products of corresponding components. Thus, the inner product measures the overlap or similarity between two vectors. The inner product is not just a mathematical operation, it has several fascinating properties. Firstly, the inner product is commutative. This means that the order in which we multiply vectors doesn't matter. We can swap them around and still get the same result. Secondly, it's linear over both the first and the second vector. This means we can multiply a vector by a scalar before or after taking the inner product, and the result will be the same. Thirdly, the inner product is positively definite. This assures us that the inner product of a vector with itself is always non-negative and zero only if the vector is a zero vector. Lastly, the inner product exhibits Hermitian symmetry. This means that the inner product of a vector with another is equal to the conjugate transpose of the inner product of the second vector with the first. These properties help us interpret and manipulate vectors in a variety of ways. So, how can we interpret the inner product of two vectors, and where is it used? Let's dive right in. The inner product can be seen as an angle measure. The cosine of the angle between two vectors is equivalent to their inner product, divided by the product of their norms. This gives us a sense of the directionality of the vectors in relation to one another. Next up, orthogonality. If the inner product of two vectors equals 0, we can say they're orthogonal, meaning they're perpendicular and do not share a common direction. A handy concept in physics and geometry, wouldn't you agree? Then there's the length of a vector. The square of a vector's norm is its inner product with itself, showing the vector's magnitude. Furthermore, the inner product helps us project one vector onto another. The projection minimizes the distance between the two vectors, and the formula includes the inner product. Last but not least, the distance between two vectors is defined as the magnitude of their difference. The inner product is a key component in calculating this. Applications of the inner product abound. In physics, it helps calculate work done by a force. In computer science, it's used in machine learning algorithms. In mathematics, it's fundamental in linear algebra and calculus. Therefore, the inner product is a versatile tool that allows us to understand and analyze vectors from different perspectives. Let's recap what we've learned about the inner product. It's a fundamental operation in linear algebra, producing a scalar from two vectors. Geometrically, it measures the overlap between these vectors. Algebraically, it's the sum of the products of corresponding components. It's commutative, linear, and satisfies positive definiteness and Hermitian symmetry. It helps to measure angles, define orthogonality, calculate vector lengths, project vectors, and find distances between vectors. With the inner product, you can unlock a deeper understanding of vectors and their applications in various fields.